Today we'll be talking about sigma notation for our Algebra 2 class. This is going to be a setup for going into an arithmetic series and geometric series, as we talked about arithmetic sequence and geometric sequence before that. So in short, let's start by introducing something called a sigma notation. Sigma notation is basically just a way to write the sum of all the terms for your sequence. So to first start, S of n represents the sum of the first n terms in a sequence of t of n. So for example, if you have a sequence that is t of n is equal to n squared, then S of 5, the sigma notation or the summation of the first 5 terms would read 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. Essentially, you're basically taking the first 5 terms and plugging it into this equation and then adding it all up. So that's what S of 5 stands for. Whereas S of r, so that means the sum of the first r terms will be 1 squared plus 2 squared plus 3 squared, all the way to whatever the r term is going to be, and you're going to add those up. So all of this right here can be represented by something called sigma notation, and sigma, the symbol looks something like this. So here's how that would actually look like then. Okay, so for the sigma notation, for n is equal to 4 all the way to 7 of 1 over n, what that means is, again, you're going to plug in values of n, which starts with the very bottom value, which is n is equal to 4, all the way to n is equal to 7. So in this case, you're going to plug 4 into the equation, and then afterward plug 5 into the equation, 6 into the equation, and 7 into the equation. So you get 1/4 plus 1/5 plus 1/6 plus 1/7, and then you add them all up, and that's going to be your answer. Now note that the sigma notation is a little bit more flexible than the summation notation right here. Whereas if you're solving for S of 5, you have to sum up the first 5 terms. Whereas the sigma notation over here, you can start wherever you want and you can also end wherever you want. So let's take a look at some examples just to see how this works out. So the first one, this is the easier problem. Solve for the numerically for the following sigma notation over here. 3n minus 4, starting with n is equal to 5, all the way to 11. So, as I said, what we're going to do is we're going to plug in n is equal to 5 into this equation, and then all the way to, n is equal to 6, 7, 8, 9, 10, and 11, and then afterward we add up all the values. So you can see that's exactly what I did over here, and I wrote out all the numbers over here. This could be either a calculator work, or if your arithmetic is good enough, then you can just go ahead and simply add it up then, for the most part. So that's not too bad. Taking a reverse step of that, because that's what math is about, we want to be able to go backwards too. That is to say, if I give you a summation of a whole bunch of terms, I want you to write it as a sigma notation. So here is an example of that. You have 3 plus 6 plus 12 plus 24, and it goes on forever. And I want you to write that as a sigma notation. Now, the idea here is that you want to write out your terms, and more specifically, I'm not going to write out the terms just using the number that's there, because I want to be able to see a pattern. So for example, the first term, it's 3. That's plain and simple. The second term, which is 6, I'm going to write that as 3 times 2 instead, because if you notice from the very beginning that a pattern over here is that you're multiplying by 2 consistently. So that's what I want to represent it as, 3 times 2. The third term, which is going to be 12, I'm going to write that as 3 times 2 times 2, or 3 times 2 squared. And then the fourth term would be 3 times 2 to the third, and so on and so on. The idea again over here is to write each term as a sequential pattern, so then that way you can come up with an equation. Now, for those of you guys that did geometric sequence already, this is not a bad thing, because that's exactly what this is. Each term is multiplying consistently by 2, so therefore we have a geometric sequence. So t of n, the term for the sequence is going to be 3, the first term, multiplied by 2, which is the ratio, raised to the power of n minus 1. So as I said, this is a geometric sequence. And that is essentially basically going to be our equation right here. So starting from the first term where n is equal to 1, and then we're going to go all the way to maybe like some arbitrary term, which we'll call k, for that equation, 3 times 2 to the n minus 1. So that's going to be our S of k then. Okay. So now let's go ahead and head into some more difficult example of how segmentation or summation actually works out. This one is a little bit more difficult. Write the sum of all multiples of 3's from 51 all the way to 300 as a sigma notation. I should have actually said that it's inclusive of 51 and also 300, so meaning that it's also including those values. So if you think about the multiples of 3's, basically the values that I want, that in itself is also an arithmetic sequence, because what's happening is for all the multiples of 3's, you're just adding 3 in order to get from one term to the next. Meaning, like say the first term is 51, the next one is 54, 57, 60, 63, and so on and so on and so on. All those numbers, as we just said, you're just adding 3 then. So then that's what I'm doing over here. I'm going to go ahead and write T of n, which is the sequence equation, and it's going to be the arithmetic sequence equation, T of 1 plus D times n minus 1. First term being 51. The difference is 3 because, again, we're looking at the multiples of 3's. And again, the idea is to come up with the equation so that way I know what is it that I'm summing. Now, the tricky part to this problem is that we know that it's an arithmetic sequence. We know that this is the first term, but we don't know what the last term is, because if you remember, going back to all the previous example, when you write a sequence equation, whenever you write a sigma notation, you need to know where to begin, you need to know where it ends, and there's also you need to know the equation. As of right now, we have the equation because it's the arithmetic sequence equation. We know where it begins because we're starting at 51, but we don't know where it ends because, well, we're just told that the term value is supposed to be 300. So what we're going to do is we're going to plug 300 into our equation to solve for what n is equal to. So put that into the equation, as you can see, and then we can solve for n, and now we know actually where it ends then. So now we can set up a sequence, now we can set up a sigma notation for this, starting with n is equal to 1, meaning the first term, going all the way to the 84th term, because that's where 300 is supposed to be. And again, you can see the work over here, of our arithmetic sequence equation, 51 plus 3 times n minus 1. Yes, you can technically simplify this, but I would like to leave it in an arithmetic sequence equation because we can actually utilize that a little bit later on. Now, your question might be, okay, do I actually have to start with n is equal to 1? Can I start somewhere else? And the answer is yes. You can actually say n is equal to 0, and then saying that in this case right here, 51 is going to be the 0th term. And what that does is it just shifts everything. So instead of starting at 1, you start at 0. Instead of ending at 84, you end at 83. But the equation itself is going to stay the same, so you can't actually alter that part. So in that sense, you can kind of change or modify the equation if you want. If you want to get even fancier, you can technically say that you start at n is equal to 11, and then you end at 94 as your 94th term for 300 over there. So where you begin and where you end, that part can be flexible, so long as you know how to modify where to begin and where to end, and how do you basically compensate for that. Okay, let's get to the harder problem. And, these are problems that basically aren't going to be in the textbook, but, it's worth mentioning because for higher learning and also for you to be able to appreciate this a little bit more. And also, just for those of you that, like math, to have a little bit of fun. Okay, so here's an example of something that's difficult. Evaluate the summation from the first term to the 50th term of the following equation. Now, this is not something that we are familiar with, meaning that it is neither an arithmetic sequence or a geometric sequence. So this is not an arithmetic series or a geometric series, meaning you're not summing something that's arithmetic or geometric. Whenever that happens, the best way to do this is just to write out as many terms as you need to, so then that way maybe you can see a pattern. Basically kind of like the same thing as what we did over here and previously. In math, that's pretty much a common or staple tool that we use. So here we go. I'm going to go ahead and plug in n is equal to 1 into this equation. And then afterward, I'm going to plug in n is equal to 2, n is equal to 3, and so on and so on and so on. Now, note that I didn't simplify it because I want to be able to kind of untangle this and see if I get something like this, something that's useful. And in fact, we actually do, because if you notice carefully, here, when you write out all the terms by just literally plugging into the equation without simplifying it, you'll see that you have a negative 1/2, positive 1/2, 1/2, negative 1/3, positive 1/3, negative 1/4, positive 1/4, and so on and so on and so on. So this string of numbers right here, in this case anyways, the pattern is that, yeah, you have a bunch of terms that get canceled out from the very beginning all the way to the very end. The only terms that are left would be then the first term and the last term. So if everything cancels out in between, then the answer to this would then be just 1 minus 1 over 51. So that right there, as I said, is going to be kind of the idea if you don't know how to approach a sequence, how to approach a series in terms of like how to solve for it if you have like so many terms to add. Here's another one, and this one, this is what's going to also lead into the next section. Evaluate the summation from n is equal to 1 all the way to 30 of this arithmetic sequence equation. So another way of saying this is S of 30, where T of n is equal to this arithmetic sequence equation. So again, I'm just going to go ahead and write out everything. And in this case, I did actually simplify each term because I think this one is going to be a little bit easier for you to see. So first, you plug in n is equal to 1, you get 5, then you get 7, you get 9, you get 11, and so on and so on and so on. In terms of where it ends, well, you're supposed to end at n is equal to 30. So I'm plugging in 30 into this equation, and then that way I can get the 63 as a result. And you'll notice that one thing that I usually like to do is I also like to write the previous terms leading into it, just in case, you know, it helps us out to see any kind of pattern for this. So here we go, from the first term, second, third, fourth, all the way to the 30th, 29th, 28th, 27th term. Now, in terms of what this adds up to be, I want to leave that to you because hopefully you can kind of see a pattern as to what's going to happen. If you want a hint as to what this is going to be equal to, think about your first number added with your last number. And then also think about your second number and your second to the last number and add those up together, and so on and so on. We'll conclude what the answer is in the next section. Okay, thank you so much.